Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 23. So, till last lecture we are discussing about this fluorescence quenching, and what we have seen is two type of quenching. In the first type of quenching, right, I said that this is a dynamic quenching, and in this type of quenching the equation what we got is looks something like this: I 0 by I is equal to 1 plus K D into concentration of the quencher. And then another type of quenching what I got is discussed is static quenching, and in this case the equation what I got is I 0 by I is equal to 1 plus K S concentration of quencher. And I was discussing about that the nature of these two plot I 0 by I and I 0 for this dynamic quenching and I 0 by I for the static quenching, they are exactly same. However, in static quenching if you plot the tau 0 by tau, you will not get any dependence, right, you will not get any dependence. This is always 1, but in this case tau 0 by tau will also give you a linear dependence with the concentration of the quencher added. Here this K D is I mentioned K Q into tau 0, where this tau 0 is the lifetime of the fluorophore without any quencher. Okay, so what is the prescription? That I have to measure both I 0 by I and tau 0 by tau if both of them are showing a linear dependency having some slope, that means having some value of K D, then this is a dynamic quenching I 0 by I or tau 0 by tau, right. How is going to measure this tau 0? This is by the lifetime method, either TCSPC or up conversion method. So, then I will get a straight line with slope is equal to K D and intercept is equal to 1. So, this is for both tau 0 by tau and I 0 by I, both for this as well as for this. However, in case of static quenching, if I plot this I 0 by I will get like this, slope will be equal to K S, here this is equal to 1, but for tau 0 by tau what you will get, the value is constant 1 even you change the concentration, and that what we have discussed, this is because of the ground state complex formation or kind of complex formation of between the fluorophore and the quencher, and because of this complex formation the system, right, will reduce the concentration of fluorophore which can be excited to the excited state. So, if I have this F, right, it is in the ground state, lambda nu excitation, this will go to the excited state. Now, if F will make a complex with Q forming F Q, which you cannot excite, right, and this is K S. So, eventually the concentration of fluorophore in the excited state, right, this is concentration of fluorophore in the excited state will also decrease, and because of this the fluorescence intensity will decrease, right, as I will increase the concentration of quencher. As I will increase the concentration of quencher, more and more F molecule will form the complex with Q. So, the availability of F for the excitation will be less. That means, the number of fluorophores in the excited state will decrease and my fluorescence intensity will decrease. This is what we have discussed. Okay. Now, we will going to look at a different phenomena. Here in this case, we will going to see what happens if both the static and dynamic quenching are present. So, here we will going to see a combined static and dynamic quenching. So, here the change of the fluorescence intensity, that is I 0 by I can write as the product of two terms. The first term is coming from the dynamic quenching and second part is coming from the static quenching. It means that the fluorophores are same, the similar types of fluorophores are present in the solution and the quencher is also same. But some of the fluorophores, that means the fraction of the fluorophores are not complexed in the ground state by the quencher, and the rest of the fluorophores which is taking part in the quenching, right, those are not quenched by the dynamic quenching. Let me write, then it will be clear. So, the first fraction is fraction of fluorophores that are not complexed multiplied by fraction of fluorophores that is not quenched by dynamic quenching. So, I can write this, the first part, obviously I know what is that. This is 1 plus k q tau 0 into concentration of the quencher and multiplied by the second term. This is nothing but 1 plus k s. This is my equilibrium constant for the complex formation, and I cannot write this k s as k q into tau 0, right, because this is a ground state. This is completely different thing. You remember this, into q. So, if I just try to simplify it, I can do that, but it is not necessary. Later on we will do that, but here you can see this is like here is my q and here is my q. So, it must be a second order in q. So, I can write a comment here, this is second order in the concentration of the quencher. And now, if you plot this I0 by I versus concentration of Q, obviously this is no longer a straight line. Obviously it will start from 1, as you can see here, when Q equal to 0. So, this whole part is 0, this whole part is 0, then is 1 into 1. So, is equal to 1. So, it will start from 1, there is no doubt, but for lower Coincher concentration it looks straight line, but as you increase the Coincher concentration you will see the curve is like this upward nature. Originally, if it is only static quenching or only dynamic quenching, then you know that the curve is a straight line where the slope value is equal to either Ks or Kd, depending on whether it is static quenching or it is dynamic quenching. So, in this case what you can see, this curve is going upward because of the second order in Q, right. The Q square term will come over here. However, if you plot tau 0 by tau versus Q, obviously you will not going to see such kind of upward curvature, because for the tau 0 of tau there is no contribution from the static quenching, only dynamic quenching is operational or is visible. Both the quenching is operational, but only dynamic quenching is visible for the lifetime measurement. So, in this case this is purely will be a straight line, intercept equal to 1, and here the slope will be equal to Kd is equal to Kq into tau 0. Let us do something so that we can get this. Let us write this as I0 by I equal to 1 plus Kd to Q to 1 plus Ks into Q. So, as I wrote, let us write it as 1 plus Kd plus Ks into Q plus Kd Ks Q square. So, this is equal to 1 plus Kd plus Ks plus Kd Ks into Q, that whole thing is multiplied by Q, and let me write it as 1 plus K apparent into Q. So, you see I got this equation I 0 by I equal to 1 plus K apparent into Q, and here the K apparent is, I can write this K apparent is equal to I 0 by I minus 1 into 1 over concentration of the quencher, right. So, now see, if I plot K apparent versus 1 over K apparent versus Q. What is K apparent? K apparent is I 0 by I minus 1 into 1 over Q. So, if I plot K apparent versus Q, what I will get? I will get simply a straight line, because here you see K apparent versus Q, if I plot, I will simply get a straight line, and the intercept will be, here you see, here is my K apparent, let me highlight it. this part, right. So, if I plot K apparent versus Q, how I will going to calculate K apparent? I will going to calculate K apparent by the measured value of I 0 and I. So, in case of K apparent versus Q, I will get such kind of equation where the intercept will be K D plus K S and the slope will be equal to K D K S. Okay. Now, the K apparent will be calculated from the measured value of I when there is no quencher, that I is equal to I 0, and in presence of quencher those values are called the I. This is nothing but the fluorescence intensity. Clear? Okay. Now, if I get this value K D plus K S and K D K S as A and B, let us say right here K D plus K S, let us say equal to A, and K D K S, because this will give some value, na? The slope this equal to B, let us say, and this equal to A, right, some value will come from the graph, K D K S equal to B, and then we can just do some simple rearrangement and we will get K S is equal to A plus minus root over A square minus 4B divided by 2, and K D will also get as A minus A plus minus root over A square, right, here A minus K S minus 4B divided by 2, which is equal to A plus minus root over A square minus 4B by 2. So, in case one, if the plus is K S, then the minus is K D and vice versa. Okay. One of them will be K S, one of them will be K D, but from the lifetime dependence, from the tau 0 by tau versus Q plot, we already know what is the value of K D. So, this is already known. So, we will calculate the value of K S. So, this is not so difficult to find out the value of K D as well as K S when there is a combined quenching, that combined means combined static and dynamic quenching. But sometime what people have found is that the value of K S obtained by such kind of procedure comes out to be too small, too tiny value. And if there is, if this equilibrium constant is because of the complex formation, right. So, this value is, this K S is F Q by F into Q. If this is a complex formation and the complex is stable, the equilibrium should be shifted to the right side. That means, in this case the value of K S should be little higher. If the value of K S is too small, that means the complex is not that stable, right, which is not so convincing to the people. So, what I was telling, that when the value of K S is too small, so probably such situation is not suitable for complex formation. So, obviously, people have started thinking then that what is the source of such kind of small value of K S. So, what we have seen here, that the value of K S is really small, and this is not suitable for the complex formation. And to explain this phenomena, that very small value of Ks, people have tried to describe the situation in a different way. Let us see that. Let us have a fluorophore sitting over here, right, and my quencher, let me draw my fluorophores like this way. Let us say this is my fluorophore sitting over here, another fluorophore is sitting over here, right, and then quencher will come and interact. Let me draw the 3 fluorophores over here, and let me draw the quenchers with this red one. So, let us say this is my quencher, just I will write Q. So, the Q will come and interact, then it will undergo this dynamic quenching, right. However, for a moderate concentration of the quencher, a situation may arise in such that the quencher molecule is present near, very near to the fluorophore molecule. This possibility is there, always there is such kind of possibility. So, let me draw such possibility here. So, here is my quencher, and let us say in this case that quencher molecule is sitting just next to the fluorophore, right. And I can imagine a situation where if the quencher is present within the volume I showed in this diagram, right. So, this is the volume made up with half of the radius of the fluorophore and half of the radius. So, radius of the fluorophore plus radius of the quencher, with that I make a volume, and I consider that if the quencher is present within this volume, the probability of quenching is unity. That means, whatever the fluorescence is there by this fluorophore, that will be completely quenched by this quencher molecule. If the situation is like this, if the situation is like this, then it is not. If the situation is like this, then it is not. So, here that particular volume is like this, right. So, that let me write in words. Let us assume the existence of a volume, and that volume I termed as V, within which the probability of immediate quenching of immediate quenching is unity, right. So, if the radius of the fluorophore is, I write as R f, if the radius of the quencher I write R q. So, that particular volume V is equal to 4 by 3 pi R f plus R q cube, right. It is about this kind of volume. Right. So, if the fluorophore is present within it, then the probability of quenching is unity. That is what I assume, right. And let me also tell that the mean number of quencher molecule within this volume V is lambda. So, I will define here that mean number of, obviously I can write later on this lambda in terms of the concentration, that will do just after a few seconds, number of quencher in the volume V, let us say I denote it as a lambda, right. Now, I can write the probability of finding just a number n quencher molecule in the given volume means that V in the given volume can be written as in terms of Poisson distribution. So, I can write this as P n is equal to lambda to the power n divided by factorial n e to the power minus lambda. This is coming from the Poisson distribution. Now, let us proceed. So, if the molar concentration of the quencher let us equal to Q, then I can write this concentration in terms of molecules per cc, right. This will be Q into Avogadro number divided by 1000. Right. So, that means the average number of molecule in sphere of volume V, that lambda is equal to V Q Na divided by 1000. Now, if I want to calculate the probability, that is no quencher is nearby, right. So, now you see this probability that no quencher is nearby, that same as according to the Poisson distribution P 0, which is equal to lambda to the power 0 by factorial lambda into e to the power minus lambda. So, I can write this as e to the power minus V Q Na divided by 1000. It means that number of observable fluoropore will be reduced by this factor, because this is P 0, no quencher is nearby, right. No quencher is nearby, that means you will get the fluorescence from that. When the quencher is nearby, those quencher will immediately quench all the fluorescence of those fluoropores. So, I want this this quantity, right, e to the power minus V Q Na by 1000, that must be multiplied with I 0. Then whatever that I 0 I will get, that is that real I 0. Then when I will add the quencher, then the decrease of the fluorescence intensity should follow my dynamic quenching, right. Otherwise, it would look like it is a combined static and dynamic quenching. So, what I wanted to say is, now if I multiply with I 0 multiplied by e to the power minus V Q into Avogadro number by 1000 divided by I, this should follow this equation. So, the I0 is modified with this quantity, I0 is modified with this quantity, that is the number of observable fluorophore, because some other has immediate in their immediate vicinity they have the quencher which immediately quench all the fluorescence. So, those I should not take care, right. So, those I should not take into account for my calculation. So, in this case is simple. Now, I0 by I into e to the power minus V into Q Na 1000, right, 1 plus Kd to Q. So, what I should plot? I should plot this one versus Q. Then what I will get? Then I will get a straight line. Then I will get a straight line, and the intercept will be equal to 1, and the slope will be equal to Kd. See that although the plot of I0, instead of this, if I had plot the I0 by I would get this type of line deviating from the linearity, and I would think that okay, this is because of the combined static and dynamic quenching, but it is not, because it is just because of the apparent static quenching, right, apparent static quenching. Okay, so let us finish here and we will continue our discussion on the next class. Thank you very much.